first speaker is Michael Hrusak, and his talk is about countably compact groups and ultrafilters.
Thank you. Very happy to be here. I wouldn't miss it for the world. So I want to talk about countably compact groups and ultrafilters, and I always forget this part. It's joint work with Jan van Meel and Ariette Ramsdassi. So let's start. So the motivation for this work is this old question of comfort, which asks about the existence of countably compact groups whose product is not countably compact, which is of course nicely contrasted to the two old facts mentioned below. The one due to Comfort and Ross, which says that products of pseudo-compact groups is pseudo-compact, and that the even older results of Novak and Teresaka show that if we drop the groups, then we have no chance that there are even countably compact spaces whose products are not pseudo-compact. And I guess the first partial or consistent result was due to Erik van Douwen, who, assuming Martin's axiom, constructed two countably compact, there is subgroups, which should be just groups, whose product is not countably compact, and later extended by Jan van Meel and Klaas Pieter, who weakened the MA to MA countable and strengthened it to just finding a one single group whose square is not countably compact. And for the last 20 years, the person who probably dedicated most effort to these kinds of questions is Arthur Tomita, so I just randomly mentioned one of his million papers where he shows that assuming MA countable, you can do all kinds of strange things. For instance, you can find a group whose square is countably compact, but the group is not. Now, what Erik van Douwen actually did was he noticed that if you have any countably compact group without convergent sequences, then inside of that group you can find two subgroups whose product is not countable. So if he satisfied with proving his theorem assuming CH, he could have just used an even older theorem of Istvan and András Hajnal, that such groups, that is countably compact groups without convergent sequences, exist assuming the continuum hypothesis. And in his paper, Van Douwen asks whether these things actually exist in ZFC. So there is an obvious relation between the two problems. If there is a yes answer to this question, then there is a yes answer to Comfort's question. Now, who proved this? I don't know. Every compact topological group has a convergent sequence. I know that, but I don't know who noticed that first. Of course, Kuzminov proved that every compact topological group is dyadic, and from that one can deduce that there is a convergent sequence, but I'm not sure who made that deduction or whether that fact was actually known before. Kuzminov, maybe somebody knows. Well, but then there are these two results I already talked about, the Hajnal and Juhasz result and Van Douwen's result. And as I said, Arthur Tomita has many papers on this topic. So in one of them, he weakens the assumption of Martin's axiom to be countable, and then he does all kinds of things. The one or the two which are interesting to us are his joint paper with Steve Watson and Salvador Garcia Ferreira, when they actually weaken the assumption to the existence of a single selective ultrafilter. So if there is a single selective ultrafilter, then there is actually a P compact group without convergent sequences, where P is that very selective ultrafilter. And in joint work with Paul, they also show that similar examples exist in the random group model. So as you can see, I tried to jam in as many of you in my first 2 slides as I could. I probably missed a few. But anyway, so all of these constructions and most of the things on this topic construct subgroups of 2 to the C. So we will be doing the same thing, but we will be doing it sort of in an indirect way. So let's start with this. So all these groups that we will be talking about are in fact Boolean groups, meaning groups where every element is its own inverse. And these groups have all very, very nice structure. They are always just isomorphic to some finite sets of some given set. So all that matters is cardinality. They are always isomorphic. And so if we take the smallest interesting one, smallest infinite, the countable Boolean groups that we denote by homeomorphisms on that groups, all group homomorphisms, all group homomorphisms from the group to the 2 element. And this naturally induces a topology of this countable group. Just by looking at the weakest topology, which makes all of these homomorphisms continuous, or simply by declaring, or the kernels of these homomorphisms sub-basis of the neighborhood filters of the neutral element. Now this gives a group topology of this countable group which doesn't have convergent sequences and is not discrete. Now, just for future use, homomorphisms on this Boolean group have very simple form. The Boolean group is a vector space, so it only depends on its values on a basis. In particular, if we take all the singletons, this is a linear basis, so that determines the homomorphism, and the homomorphism is just look at all the basic elements which have value 1, so gather them in a set A, and then the homomorphism is just the parity of the intersection with that set. So what the plan is to take this countable group, which doesn't have convergent sequences, and enlarge it in such a way that it will become countably compact. And actually, at least in the first half of the talk, we will do it in a definable way. So we'll just take one ultrafilter, we define a bigger group, we define a topology, and then we just ask ourselves, when is this topology, when does it have the property that it doesn't have convergent sequences? So how do we do that? Well, we just look sort of at abstract p-limits. So if I have my group, I take a sequence of elements in this group, I want to give it a p-limit. So how do I do it? Well, the natural thing is look at the ultrapower, look at the equivalence class of that very sequence, and declare that the p-limit of that sequence is its equivalence class. Okay? Well, then every homomorphism on the small group naturally lifts to a homomorphism, extends to a homomorphism of the bigger group. How do I do it? Well, by this formula, I just declare the homomorphism of the equivalence class of a sequence to go with the majority of its values. Right? It has values 0 and 1 on each element of the sequence. The ultrafilter tells me what is the majority, and that's the value I give to the limit. Right? Well, okay, so now I can extend these homomorphisms, and I can use the topology generated by these extensions on the ultrapower. Okay, so it's a bigger group. But now what did I do? Well, I made sure that every sequence in the small group has a p-limit in the bigger one. All right, now I can iterate. So I will iterate this process omega-1 many times. Okay, so I did it once, I get a bigger group, and every sequence in the smaller group as a p-limit, then I do it one more time, and omega 1 many times. And now what do I get? Well, I can keep extending the homomorphisms that I started with in the very same way, and therefore I can define the topology on this omega first ultra power. Well, I don't have on this omega first ultra power induced by all these extensions of these homomorphisms. Okay. And now this is a p-compact group because I never separated a sequence from its p-limits. All these extensions had the property that they respected the p-limits. So this is a p-compact group no matter what ultrafilter I start with. Okay. And also, rather than iterating the ultra power construction, I could just look at, rather looking at p-limit, I can look at p-alpha limits for the alpha Fubini power of the ultrafilter P. So it just, from the sequences down there, I can get higher and higher and higher just by changing this ultrafilter, looking at these higher powers of it. All right, so now the natural question is, when, if ever, this group is one of the ones that I'm looking for, right? Well, assume for a while that this is a Hausdorff topology, which is not a given. So if it were a Hausdorff topology, then by the simple construction it cannot have convergent sequences, because we know that the classes are distinct things, and they are always inside every infinite set. I can find many sequences which are not equivalent. So we couldn't have convergent sequences. And moreover, one can naturally characterize, at least going from the very bottom level to the first level, what happens? Well, there, the ultra power of P is Hausdorff if and only if the ultrafilter has this property, and it essentially just says that if there is, for every sequence, there is a homomorphism which gives to that point value 1 and to 0 value 0. Well, so this looks like a very nice characterization. There is a problem with it, that it only works on the first level. It doesn't work 2 levels up. So for 2 levels up, you are never Hausdorff. And essentially the thing is that if you look at P squared, you have 2 projections, the one to the left and the one to the bottom, and they cannot be separated by homeomorphisms. Okay? All right, so that was the first attempt. Let's try the second one. Well, because of the nature of how we define the topology, if you look at the intersection of the kernels, that's going to be a closed subspace, and that's exactly those things which cannot be separated. So if we factor by this closed set, which happens to be a closed subgroup, we get a nice Hausdorff, separable, p-compact, non-discrete zero-dimensional group. However, that argument which I said that Hausdorff was good enough for killing convergent sequences is no longer true, because I don't know how big that kernel is, that this K is. Well, but still, I can give a combinatorial characterization of that ultrafilter, which tells me essentially literally, if you look at what's written over here, it tells me literally, if I take a sequence of things which are not equivalent, which is the thing which says that they are p-separated, then it's not convergent because one of the homomorphisms splits it into 2 infinite pieces. So it really is nothing spectacular. This is just a straightforward translation. But it's helpful to say, well, okay, so which ultrafilters are these? And also, if one makes a little tweak to it, then it's actually a characterization. So it tells exactly which ultrafilters give countably compact subgroups of 2 to the C, which do not have convergent sequences. Well, this is what I should have said is this is all very much a work in progress, so I'm going to tell you a lot of half-baked ideas which we didn't follow through. So all of this essentially follows what Garcia Ferreira, Watson, and Tomita were doing in their papers, even though they somehow didn't choose to do it this way. They have some recursive construction which I couldn't quite follow, but I think it's the same thing as what I'm talking about here. And in particular, an a Ramsey or selective ultrafilter has this property that I just mentioned. But I would like to introduce an intermediate property, which we will use later on. And that's the one which is down here. So if I have a, so what is the sequence of p-independent functions? Well, it just means that if I look at the first level of the group, then they are independent in this ultra-power group. So it's just linear independence.